Howdy folks, this long-form discussion is going to be all about Walter Baade and Fritz Zwicky's work published in 1934 on the topic of supernovae. It's in this work that supernovae are not only identified for the first time, but the finer details of the supernova process are also theorized for the first time. Along with that, Baade and Zwicky also predict for the very first time the existence of a population of ultra-dense, ultra-compact stars that they call neutron stars. This discussion is going to be much more of a high-level discussion, and I'm not going to get into the finer details of the physics or the mathematics used by Baade and Zwicky in this work. That said, I have provided references for the pair of papers by Baade and Zwicky published in 1934 right now on the screen, as you can see, but they are also more importantly in the description, since those references contain DOI information and links to where you can access both of these papers under free and open access from the publisher, at least at the time of posting this discussion in April of 2025. Both papers are only about 5 or 6 pages each, and if you want to get into the finer details or the physics and mathematics of Baade and Zwicky's work, I would strongly encourage you to go and get access to those papers and read through them, since they are relatively short, but dense nevertheless. This discussion is going to be largely audio only, so feel free to kick back, relax. There's not going to be too much that you're going to have to pay attention to on the screen, unless for whatever reason you want to. But with that said, let's dive into Walter Baade and Fritz Zwicky's work published in 1934 on the topic of supernovae. Alright folks, so I think the best place to start is not actually with Baade and Zwicky's work on supernovae or their pair of papers, but rather I want to use the benefit of hindsight to go back and look at some of the relevant discoveries and proposed ideas that came from the first third of the 20th century, 1900 to 1933. And I think that's going to be really important and useful because there was a heck of a lot of new discoveries, revolutionary discoveries, and not just new ideas, but very, very profound ideas being proposed in the first third of the 20th century, especially in the fields of astronomy and physics or astrophysics. So I have a short list here of what I think are some important discoveries and also proposed ideas that are very relevant to Baade and Zwicky's papers on the topic of supernovae, and thus also are very influential, if you will, on their proposal for the existence of ultra-dense, ultra-compact stars, mostly made of neutrons, they call neutron stars. Now, before I start going through this list of things, I just want to quickly say that none of this discussion is scripted at all. I have a rough outline in my head of what I want to talk about and in what order, and with this short list that I have, these are just rough years, so I don't want anybody to go citing this or anything else. The whole point of this is just to highlight some of these new ideas that people are considering or thinking about, and some of these new discoveries as well that are changing the way that people are thinking about things that may impact their own work in astronomy or in physics or cosmology, anything related to that, really in astrophysics. So in this first third of the 20th century, the year 1900 to 1933, you have things like in 1905, Einstein with special relativity. In 1911, you have Rutherford with the discovery of the nucleus. So we didn't even really have a full picture 23 years prior to Baade and Zwicky's paper on the actual structure or configuration of an atom. Between 1911 and 1913, you have Hertzsprung and Russell, two astronomers that come up with what is now known as the Hertzsprung-Russell diagram. They both do this work independent of one another of creating this Hertzsprung-Russell diagram that shows us things like the main sequence, shows us populations of white dwarfs and other giants, and understanding stellar evolution and things like main sequence stars and the different classifications that they fall under and the evolutionary tracks that they follow is a very novel idea as well. There weren't too many people that were considering stellar evolution prior to this, or at least it wasn't as concretely understood through things like the Hertzsprung-Russell diagram. In between Hertzsprung and Russell in 1912, you have Victor Hess, who is conducting balloon experiments. He's taking things and strapping them onto balloons, sending them up into our atmosphere, right up to the edge of space, where he discovers cosmic rays. Okay, these are particles that are traveling nearly at the speed of light. They are highly, highly, highly energetic, and that also completely changes the way that people are all of a sudden now thinking about our universe. Largely because there are people who cannot wrap their heads around why there are these particles that we are detecting that are so highly energetic. Then in 1915, you have Einstein with general relativity, which obviously we can't ignore. It's Einstein's biggest theory, if that's what you want to call it. That's what many people say, at least anyways. Now, I'm not going to go into a full spiel on general relativity, but obviously we cannot have a conversation about ultra-compact objects or ultra-dense objects without an understanding of general relativity. And I should also mention that this was not very well accepted, and Einstein, I don't want to say wasn't very well respected, but a lot of people saw him as a bit of an eccentric, and as a result, people did not really accept general relativity all too terribly well. In 1917, you also have Rutherford discover the proton, so now all of a sudden, 6 years after discovering the nucleus of the atom, we're kind of starting to deconstruct the nucleus and figure out, well, at least we have figured out one half of the atom at this point in time. And after that, in 1919, it doesn't take too long for one Arthur Eddington to observe light bending, which was really confirmation that Einstein was onto something with general relativity. The 1920s is quite a revolutionary decade for the fields of physics and astronomy. In physics, you have quantum physics emerge out of this. All the big key principles and concepts that we understand with quantum physics really come out of the 1920s. I'm talking, of course, about things like the de Broglie wave. I'm talking about the Schrödinger equation, the uncertainty principle, the Dirac equation. But along with that, you also have an emergence of so much more understanding of our universe in astronomy, especially with a lot of the work from Hubble. Hubble in the 1920s proves the existence of extragalactic objects, or basically, he is looking at a lot of the other galaxies, he's looking at a lot of the other things and saying, hey, those things do not exist within our own Milky Way. Those objects are outside of our own Milky Way, and those are galaxies in of themselves. And as we'll see with some of the vocabulary and the terms and the discussions that Baade and Zwicky have, they still refer to the Andromeda Galaxy as the Andromeda Nebula, which really just goes to show just how new of an idea or an understanding it is that there are objects, there are things that are existing outside of our own Milky Way. Along with that, in the first half of the 1920s, you have Alexander Friedmann propose that our universe is expanding. So it's quite a big cosmological proposal, but then by the end of the 1920s, you actually have Hubble confirm this. So you are seeing now big leaps and bounds, revolutionary ideas, revolutionary discoveries happening, not just to our understanding of stars, but of our entire universe as a whole, with these extragalactic objects, and then also that our universe is expanding. To go along with that, during this period of time, you have the Belgian priest and scientist Georges Lemaitre develop the Big Bang Theory, or propose the Big Bang Theory. And so now all of a sudden people are all of a sudden thinking about not just stellar evolution, but they're thinking about the evolution of our entire universe as a whole as well, which is completely a new idea and a new thing for people to be considering in cosmology or astronomy and astrophysics. And then in the 1930s, between 1930 and 1933, you have the discovery of the positron. Then you also have the discovery of the neutron to complete our full view of the nucleus of the atom. And of course, we cannot have a conversation or the prediction for the existence of neutron stars if there is no discovery of the neutron and also some of the properties of the neutron. So folks, that is where my list ends. Now, what I hope you got out of that short use of hindsight and going over some of those new ideas, some of those new discoveries that came about in the first third of the 20th century. I hope that you really see just how revolutionary a lot of those new things are. Okay, it's completely changing the way that astronomers are thinking about our universe. It's completely changing the way that physicists are even thinking about doing physics. When you think about quantum physics, for example, all of a sudden they're quantizing things. They're realizing, I mean, they'd known for a little bit that there were some limits to classical physics, but now we're quantizing things and now we're able to explain new things that we weren't otherwise able to explain before. And so there is this revolution, there is this renaissance even, in physics and astronomy in this first third of the 20th century that definitely impacts Walter Baade and Fritz Zwicky's thinking and influences their work on the topic of supernovae, which leads to that prediction of the existence of neutron stars. And as far as I can tell, Baade and Zwicky's work, published in 1934, is the first time that a supernova as a concept is even proposed or even referenced. And so with that, their first paper titled On Supernovae is really just them laying out what is a supernova, why do we know that these things exist, and what are some of the key properties that make up this supernova. But how exactly do Baade and Zwicky come up with this idea, or even come to this understanding that we even need to have the concept of a supernova even proposed? How did they come up with this idea? And really, it's quite interesting because they go ahead and they look at novae, which are the appearance of new stars in the night sky, these transient events where we see a big bright flash and the appearance of a new star at some point in the night sky. And they look at a long-running history of these novae. And what they realize is that based off of the luminosity or the brightness of these novae events, there are two very distinct classifications of novae that they observe. The first classification they call common novae, because out of all the novae that they are considering and that they're paying attention to, they realize that a majority of these novae that they are considering fall into this first classification. Therefore, they call it common novae because they seem pretty common. These things tend to occur quite often, and they recognize that this first class of common novae has a much lower luminosity than the second class. I shouldn't really say luminosity. What I more so mean is maximum brightness. Maximum brightness, which, with all of these novae, they occur over a period of days, and they build up to being brighter and brighter and brighter, and then they eventually start to dim out over a period of time. And so in the case of these common novae, they note that these common novae reach a maximum brightness of about 5 mags. I don't have the exact number in front of me, but I know that it's somewhere between 3 to 5 mags. Let's just say 5 mags for the sake of argument. And it's in this maximum brightness that they really see the big difference, the big split between these two classes of novae. The second class is what they call supernovae. It's actually what they propose as supernovae because, again, as far as I can tell, this is the first paper where the concept of a supernova is proposed. And they say that the maximum brightness that these supernovae events are getting to are almost quite literally as bright as the galaxies in which they are originating from. And they also note that Hubble has gone ahead and taken an average brightness of a lot of these different galaxies outside of our own Milky Way galaxy, and he's found that they have a brightness of around 15 mags, okay? And these supernovae, at their brightest, end up being about 13 mags. So, quite literally, they are almost 3 times as bright as common novae, and that's the key differentiating factor between common novae and supernovae. This is what they say, and this is, they also mention there's nothing in between the common novae and the supernovae. There's the common novae. We see a lot more of them than we do the supernovae. Those common novae reach a maximum brightness of about 5 mags, and the supernovae, well, they're reaching a maximum brightness of about 13 mags, and there is nothing else in between. There are no novae that are like, 8 mags, 10 mags. There's no noticeable population of other novae. And so this is where they come up with this second classification. And as a matter of fact, I think that Baade and Zwicky really do a good job of clearly describing these two different classes themselves in their first paper, published in 1934, titled on supernovae. And so we'll start off, I'm going to give you the exact quote of how Baade and Zwicky describe common novae, and then I'll give you the exact quote of how Baade and Zwicky describe supernovae, or at least what they propose as supernovae. And so Baade and Zwicky first describe common novae as, quote, "Common novae seem to be rather frequent phenomenon in certain stellar systems. Thus, according to Bailey, 10 to 20 novae flash up every year in our own Milky Way. A similar frequency, 30 per year, has been found by Hubble in the well-known Andromeda Nebula." End quote. They then describe the second class of what they propose to be called supernovae as, quote, "The novae of the second group, supernovae, presented for a while a very curious puzzle because this type of new star was found not only in the nearer systems, but apparently all over the accessible range of nebular distances. Moreover, these novae presented the new feature that at their maximum brightness they emit nearly as much light as the whole nebula in which they originate." End quote. As I've already stated, I think both of those descriptions are very, very clear as to some of the differences between common novae and supernovae. But one of the things that I really want to highlight out of both of those quotes is how Baade and Zwicky are using the term nebulae, especially when they are referring to Andromeda. You have to remember that this is 1934, and it's been about a decade, maybe a little bit more than a decade, since Hubble had proven that there are galaxies that exist outside of our own Milky Way. Maybe I'm reading a little bit too much into their use of this vocabulary, but I think it just goes to show just how new of an idea still the concept of a galaxy outside of our own Milky Way really was at that point in time in 1934 when Baade and Zwicky are writing this paper on supernovae. And so with the identification of these two very distinct classifications of novae, Baade and Zwicky want to all of a sudden start to flesh out, okay, what actually is this supernova? What are these supernovae that we are observing? What is this second class, this class of novae that at their maximum brightness is so much brighter than common novae and so less frequent? And so to accomplish this, Baade and Zwicky all of a sudden want to develop some kind of timeline to get a better understanding of what these supernovae are. What was there in the night sky where a supernova occurred before the supernova occurred? What was there after the supernova kind of faded away? And then, of course, we could see, obviously, the supernova event as it got brighter and brighter and then began to dim out. And so what is that process? What's happening when we build up to that big brightness, and then what happens when it's fizzling out? This is what they want to kind of try to describe, because we see these things. We see the supernovae. They've identified this, the second classification. So what exactly is happening at the beginning, at the end, what's happening in the middle? These are the types of things that Baade and Zwicky try to answer with this paper. And rather unfortunately or annoyingly for Baade and Zwicky, they realize that almost all of the supernovae that they have from their classification of these novae events have actually occurred outside of our own Milky Way. And that presents a number of problems, obviously, because they're occurring in other galaxies, and it's quite hard to resolve the details of what was possibly in that part of the night sky in those other galaxies, and it's even going to be even more difficult to figure out what is left over after the supernova event, again, in these other galaxies, especially, again, when you consider that this is all happening in the 1930s. But it's actually not too bleak for Baade and Zwicky, because in some cases, they actually can see some of the individual stars that are in these other galaxies, but more importantly, they notice something very interesting about where these supernovae are occurring. And with that, they say, quote, "Supernovae occur not only in the blurred central parts of nebulae, but also in the spiral arms, which in certain cases are clearly resolved into individual stars." End quote. And so with that, they pick up on the fact that these supernovae can pretty much occur anywhere within a galaxy. It doesn't matter if they're in the spiral arms or what they call the blurred central regions, okay? It doesn't matter. These things can occur anywhere within a galaxy. And with that, they note just how similar some of these other galaxies are with their spiral arms and overall shape and appearance to our own Milky Way galaxy. And so they say, therefore, it's conceivable that we will, and probably have, observed a supernova in our own Milky Way at some point in time. And so they go looking through older novae that were observed that could have potentially been supernovae, because the catalogs that they're going off of, they're not like super old catalogs, but they're fairly newer because they're getting actual measurements of, of course, the brightness to make these classifications between common novae and supernovae, or just, much more common and less bright at its maximum versus very, very bright at its maximum in the case of supernovae. And they realize that there is one nova event that stands out as potentially being a supernova that was observed in our own Milky Way galaxy. And that nova is what is called, or what is known as, Tycho Brahe's nova of 1572. Now, it's called Tycho Brahe's nova because it is named after the Danish astronomer who is the first one, or probably really just the most well-known individual to document this nova in 1572, and that would be the Danish astronomer Tycho Brahe. Now, supernova 1572, or Tycho Brahe's nova, is really important because based upon where it was noted as being observed in kind of our night sky by Tycho Brahe, it becomes pretty clear that it is very likely that this nova was one that occurred in our own Milky Way galaxy. And along with that, Tycho Brahe also noted that this nova was abnormally bright. It was much, much brighter than any of the other novae that he had observed before. And this is a very important point, of course, for Baade and Zwicky, because now with this understanding that they've come up with here of these two distinct classifications of novae, and the fact that the second class of supernovae is much less frequent, in other words, much more rare to observe, they come to the understanding that it's probably pretty likely that Tycho Brahe's nova was in fact a supernova. And to go along with that, now all of a sudden, they have an area of the night sky in which they can look at themselves and see what's there, in 1934, but they can also look through archives and records of what has been in that part of the night sky previously. And if they're really lucky, they could look back in very, very old records and archives and potentially see what was in that part of the night sky before Tycho Brahe observed this abnormally bright nova there. And so after going through archives and records of that patch of the night sky that Tycho Brahe recorded that nova occurring in, Baade and Zwicky have the following to say regarding supernova 1572. They say, quote, "The supernova of 1572 in its initial stage probably was not brighter than apparent magnitude 5, as otherwise it would be registered as such in the old catalogs, which, however, is not the case." End quote. So, in that patch of the night sky before Tycho Brahe's nova, so the initial state of whatever is there beforehand, which is whatever caused or whatever was involved in Tycho Brahe's nova, couldn't have been anything other than some ordinary star. Because if there was something interesting or unique or special there, it would have been noted as such. That's basically what Baade and Zwicky are trying to get at here. And so, obviously in today's day and age, most people would then assume probably a main sequence star. If I were to just tell you to consider some ordinary star, you'd probably consider a main sequence star, considering just how prevalent they are in our universe. But this is really significant for Baade and Zwicky because now they have some initial state that they can use or work with. And getting an end state of Tycho Brahe's nova is not particularly difficult because there's a whole bunch of historical records that they can go off of, based off of observations of that patch of the night sky since 1572, or, worst case scenario, they could just go and take a look with a telescope on their own and see what's in that patch of the night sky. There's a pretty good chance that not too much has probably changed between 1572 and 1934 that would dramatically change the perception or the understanding of what was left over after Tycho Brahe's nova fully dimmed out. But they don't really find any clear, distinct object as the remnant left over, or whatever was left over after, the supernova event. So they jump to, okay, what happens during the actual supernova? What does that process look like? And on that, they say, quote, "A common nova reaches maximum brightness in about 2 to 3 days. Indications are that a supernova reaches maximum brightness during about the same interval." End quote. Okay, so with that said, let's summarize what Baade and Zwicky have to work with here, because really the bulk of this paper is going to be them taking the initial state, the end state, and then what they know about the supernova in the middle, mainly how long it takes to reach its maximum brightness. And they're going to take all of that and they're going to do a whole bunch of theoretical astrophysics. They're going to compute a whole bunch of things based off of the temperature or perceived temperature, based off the luminosity. They're going to go off of the radiation involved and also the energies involved with this to try to arrive at some conclusions to try to describe what exactly is going on with this supernova. So initially, we have that there must be some type of common star there. In today's day and age, we would probably just say a main sequence star, so some type of ordinary star, fairly common star, right? We know that the supernova will reach its peak brightness in about 2 to 3 days, and there isn't any type of identifiable object or anything left over after the supernova. Obviously now, in today's day and age of 2025, we know about supernova remnants, but Baade and Zwicky don't know this yet at this point in time. So they're kind of flying blind, if you will, into what the end state of a supernova is. But as I just mentioned, Baade and Zwicky are going to go through, they're going to do, take these conditions that they have, and they're going to do some astrophysics, again, using luminosity, using temperature or assumptions of temperature. They're going to go based off of course, using that duration of 2 to 3 days to reach the peak brightness. They're going to go off of the maximum brightness. In the case of supernova, that's going to be about 13 mags. And they arrive at two conclusions, taking all of that into account, computing radiations, computing energies. They arrive at two conclusions of what a supernova is, or what's actually happening during the process of a supernova. And their first idea for what is going on in a supernova, they describe as, quote, "The phenomenon of a supernova represents the transition of an ordinary star into a body of considerably smaller mass." End quote. And the second case that they present is with the consideration that they may have potentially overestimated the effective temperature used in their computations. And so if they overestimated the effective temperature in their computations, they say, quote, "Energy of the trapped radiation alone is comparable with energy of total annihilation of the star." End quote. And so with that second case, Baade and Zwicky are proposing that the star just completely annihilates. Which of these two cases do they think is more realistic? Well, they make it pretty clear that they think that the first case of the ordinary star transitioning to being a body of much smaller mass is far more likely than just the complete annihilation of the star, because again, that second case is really just there if they overestimated the effective temperature of the supernova, which they don't really think that they overestimated, but just in case, they're throwing the second case in here. And so that is really Baade and Zwicky's initial proposal for what supernovae are. This first paper they published in March of 1934, titled On Supernovae, is quite literally just them describing or laying out their understanding of this much rarer and much brighter classification of novae that they call supernovae. And in doing so, they take a look at, okay, what do we know about the initial state, or what is there that we could potentially know about the initial state? What do we know about the end state? What do we know about what's going on in between? And then it's just them doing some theoretical astrophysics to figure out, okay, what is actually happening during a supernova? And it's from there that we get their two cases of either that it's an ordinary star transitioning to some smaller mass, or it's just the star completely annihilating. Now, obviously, we have the benefit of hindsight, and we now understand that Baade and Zwicky are pretty spot on with their first initial case that they present. But it's not the only paper that they publish in 1934. As I previously mentioned way at the beginning, they published two papers in March of 1934, both on the topic of supernovae, and this is just the first paper. I'll encourage you to go ahead and check out the citation and read this paper for yourself. It's only about 5 or 6 pages long, and if you have just a small understanding, or if you've done any bit of undergraduate astronomy or astrophysics, you could probably begin to start to understand some of the computations that they are doing and some of the theoretical astrophysics that they're doing. But this paper, titled On Supernovae, is, as far as I can tell, the premier or initial paper of where the concept of a supernova is not just presented, but also kind of fleshed out a little bit. And so, of course, for that reason, I find this to be a really impactful and very important paper in the world of astronomy and astrophysics, especially for anybody that studies supernovae or anything related to supernovae, like in my case, neutron stars, pulsars, and magnetars. Here's the thing, though. It's pretty clear to me that Baade and Zwicky had been sitting on this understanding of this second classification of novae for quite a while, actually. And that's because they didn't just identify this second class of novae they call supernovae. They actually took the time to sit down and think about some of the implications of their understanding of this second class of novae. In other words, they developed some ideas for what the existence of these supernovae means to the rest of the universe. To put it bluntly, Baade and Zwicky clearly thought about if their understanding of the existence of supernovae helped answer any other open questions or concerns in astronomy, astrophysics, or cosmology. Or even moreover than that, did this understanding of the existence of supernovae help develop an even better understanding of existing knowledge in astronomy, astrophysics, or cosmology? And what tells me that Baade and Zwicky had been sitting on this knowledge of the existence of supernovae for such a long time is that they actually find an open question that supernovae helps provide a little bit of an answer to. And that question is, where do cosmic rays come from? And hence, that is why in 1934, they publish a pair of papers on the topic of supernovae. They don't just publish their paper titled On Supernovae, presenting their understanding of this second classification of novae that's much less frequent, that's much brighter, that they call supernovae. They publish a second paper immediately after this paper introducing supernovae to the world, and that paper is titled Cosmic Rays from Supernovae, where Baade and Zwicky lay out their case for why they think cosmic rays originate from supernovae. Now, if you'll recall from the beginning of this discussion, in 1912, Victor Hess doing balloon experiments up basically at the edge of our atmosphere, basically in space, but pretty much at the edge of our atmosphere, where a lot of people, still do balloon experiments today. Victor Hess, doing these balloon experiments, discovers cosmic rays, very high energy particles, basically in space, but at the edge of Earth's atmosphere. The problem is that since 1912, nobody had really been able to figure out really any of the origins of these cosmic rays. Now, don't get me wrong, there were still plenty of people researching these cosmic rays. As a matter of fact, there were plenty of other experiments that were done to measure cosmic rays or observe cosmic rays between 1912 and when Baade and Zwicky are writing this paper in 1934. But nobody really had any concrete explanation or understanding of where these cosmic rays could be coming from. And before Baade and Zwicky start their proposal that supernovae are a potential origin of cosmic rays, they take stock over what has already been established as fact regarding cosmic rays. In other words, what were we able to already establish through observation about cosmic rays? Baade and Zwicky note that measurements of the intensity of these cosmic rays actually yielded a dip in the intensity measurement when the cosmic rays were interacting with the Earth's magnetic field near the equator of our planet. Baade and Zwicky determine that this observed dip in the intensity of cosmic rays has to mean that these cosmic rays, with as high energy as they are, must have come from a very, very long way away, meaning that these cosmic rays must have traveled an extraordinarily far distance. To go along with this observation of intensity, they also note that cosmic rays' intensity has absolutely nothing to do with time, and if it did have anything to do with time, well, then that would mean it's very likely originating from somewhere close by, like our sun or some other star, or something in our own Milky Way galaxy. And so these two facts regarding the intensity of cosmic rays leads Baade and Zwicky to come to the understanding that these cosmic rays that are being observed must originate extragalactically, meaning outside of our own Milky Way. But you see, there's a problem that Baade and Zwicky have with this, because really, if this is true, that the origin of these cosmic rays must be from something extragalactically, well, it doesn't really make a whole lot of sense that they would be coming from another galaxy, because as they mentioned in their paper on the topic of supernovae, a lot of the other galaxies are remarkably similar to our own Milky Way galaxy. And so if we haven't observed or found the origin of cosmic rays in our own Milky Way, why would we expect to find them originate from some other galaxy, like, say, for example, Andromeda? And so since that line of reasoning doesn't really work, there isn't really much else to go off of with regards to answering the question about where these cosmic rays might originate from. But Baade and Zwicky have the following to say on that matter. They actually have two potential hypotheses before they even jump into considering supernovae. They say, quote, "One arrives, therefore, at one of two hypotheses, either that cosmic rays originate in intergalactic space, or that they are survivors from a time where physical conditions in the universe were entirely different from what they are now." End quote. And at the end of that quote, they cite Georges Lemaitre. Remember, again from our history section, that is the Belgian priest who developed the Big Bang Theory. And here's the thing, both of those hypotheses, as far as Baade and Zwicky are concerned, are pretty poor hypotheses, and to be completely honest, I'm in a bit of agreement on that matter. I think Georges Lemaitre's Big Bang Theory definitely provides a little bit, it makes a little bit more sense than that these cosmic rays are somehow originating from intergalactic space. I mean, there's, as far as we can tell, nothing in intergalactic space. At this point in time, we don't know anything about dark matter, dark energy, so, okay, maybe these cosmic rays have something to do with dark matter and dark energy in today's 21st century, 2025 thinking, but probably not. I mean, there's no evidence to suggest that, so why would anybody in their right mind, especially in 1934, think that these cosmic rays are somehow originating in the middle of nowhere, where as far as we can tell, there is nothing out there? And Georges Lemaitre's Big Bang Theory isn't that much better of a hypothesis. I mean, it's slightly better if you consider that, there's this Big Bang at the initial creation of a universe, and obviously Big Bang, very energetic event or series of events, if that's what you want to think of it like. But really, we're going to chalk up all of these cosmic rays that have been observed to the very origin of our universe. They've just been, out there forever? There's not much convincing evidence to support that. Especially in 1934, when Baade and Zwicky are thinking about, and not just Baade and Zwicky, but numerous other physicists, astronomers, astrophysicists, are thinking about where the heck are these cosmic rays produced? How are they out there? How are they able to even be observed? And so with regards to cosmic rays, at this period of time, 1934, we know they very likely originate somewhere extragalactically. But since we don't observe them at all in our own Milky Way galaxy, it's very unlikely that they are coming from any of the other galaxies that are very similar to the Milky Way. There's next to no evidence at all that they're originating from intergalactic space. And really the best explanation is that they're a byproduct of the Big Bang. Baade and Zwicky have a different idea after considering all of this, and on that, they propose that cosmic rays originate from supernovae. I know, what a surprise, right? After all, the title of their paper is Cosmic Rays from Supernovae. But the way that they present the possibility that these cosmic rays originate from supernovae is actually, I think, quite interesting. And so they present supernovae as a potential origin for cosmic rays as, quote, "It has been concluded that extragalactic nebulae cannot be the centers of production of cosmic rays, as no such rays seem to originate in our own galaxy. If, however, the production of cosmic rays is related to some sporadic process, such as the flare-up of supernovae, the above-mentioned difficulties disappear." End quote. And then, of course, later on, not too far along in the paper, they outright say, quote, "Cosmic rays are produced in the supernova process." End quote. So they make their point very, very clear on the matter that they think that cosmic rays come from supernovae. And the rest of this paper is them actually computing what the intensity of such particles would be if they were to actually originate in the supernova process. And rather interestingly enough, their computed value for the intensity of such rays from a supernova, if they were measured here by humans on Earth doing, say, balloon experiments, and the computed intensity that they have theoretically agrees incredibly well with the observed measurements of the intensity of cosmic rays that were actually done with the balloon experiments. And so, again, just like with the first paper titled On Supernovae, the second paper titled Cosmic Rays from Supernovae is also referenced, and I would strongly encourage you to read it. Again, it's only about 5 or 6 pages long, and I'm not going to go through all the math for you. You need to read the paper for yourself and see this for yourself. But I just want to point out and mention the two values, the actual measured intensity of these cosmic rays, and Baade and Zwicky's computed value from theory. The observed value is 3.53 times 10 to the negative 3 ergs per centimeter squared seconds. I really hope I got those units right. I've almost certainly messed them up, but we'll see how this goes. But anyways, the computed value that they get is 3.2 times 10 to the negative 3, and that's what matters. It's the same units. So the observed intensity is 3.5 times 10 to the negative 3, and from doing everything from theory, assuming that the origin of these cosmic rays, or that these cosmic rays are produced from supernovae, yields a value of 3.2 times 10 to the negative 3. So you're talking about just a couple of decimals difference between theory and observation. Of course, Baade and Zwicky have way more to say They present quite a bit in this paper, and that's as much as I want to discuss. Because as far as I'm concerned, just how close that theoretical value is to the observed intensity of cosmic rays is strong enough evidence for me, especially considering all the other possible explanations. These things are almost certainly not originating from intergalactic space. There's next to no evidence for that. I think it's fair to say there's no evidence for that, but next to no evidence, because I want to always, leave the door open just a little bit. Sure, these things could be remnants of the Big Bang, but personally for me, I don't even know how I would go about trying to prove that theoretically or observationally. It's going to be difficult one way or the other. I'm sure somebody's tried, and I'm sure there's a paper I'm missing out there, or at least a couple of papers that I'm missing on the matter, but I don't even know where I'd begin on that matter. And it certainly makes a great deal of sense that we would think that other galaxies could not be the sources of these cosmic rays if we didn't observe them at all in our own Milky Way, due to the striking resemblance and similarities that our own Milky Way galaxy has to other galaxies. But with that, it also makes a ton of sense that perhaps the reason why we're not seeing the origins of these cosmic rays in other galaxies is because in just the paper before this one, Baade and Zwicky paint the whole picture of that new class of novae called supernovae that is very rare, happens very infrequently, and is very transient in that it flashes up, it's only around for a couple of days, and then it dims out. And if that's where cosmic rays are produced, then it makes sense why, up until this point in time, nobody's been able to figure out where cosmic rays are produced. Now again, I will say that I have both of these papers referenced, so you can go and you can check them out for yourself. Both papers are available under open access, so please do go read them, because I am leaving out quite a lot. So not only have Baade and Zwicky identified this new class of supernova, but they've fully fleshed out what a supernova is, and they've provided a pretty good explanation of what they think is happening with a supernova. And they've gone ahead and they've used that and applied that to help explain, or at least provide a possible solution to one of the problems that is existing elsewhere in astronomy and astrophysics, which is the problem of the origin of cosmic rays. But it's not just their prediction that cosmic rays come from supernovae that comes out of this paper titled Cosmic Rays from Supernovae. Because you see, at the end of this paper, again titled Cosmic Rays from Supernovae, in some closing additional remarks, they make another prediction that is very impactful and very meaningful to pretty much all of the work that I do. They go ahead and they predict the existence of a new type of star, a star that they call a neutron star. And the exact way they make that prediction is as quote, "The new problem of developing a more detailed picture of the happenings in a supernova now confront us. With all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. Such a star may possess a very small radius with an extremely high density. As neutrons can be packed much more closely than ordinary nuclei and electrons, the gravitational packing energy in a cold neutron star may become very large and, under certain circumstances, may far exceed the ordinary nuclear packing fractions. A neutron star would therefore represent the most stable configuration of matter as such." End quote. This is a very bold claim or prediction by Baade and Zwicky, and from these papers they have at least a little bit of evidence for this, especially with their prediction that the goings-on, at least within the process of a supernova, is very likely a transition of some larger mass to some smaller mass. But they also, of course, predict from the work they present in their first paper, that the supernova process could just be the annihilation of a star. And they basically conclude their final remarks of the paper titled Cosmic Rays from Supernovae by basically saying, we don't have the space or the time necessarily right now to flesh out this entire idea of a neutron star, because that's not necessarily the focus of their papers here. But nevertheless, it's in this way, in closing additional remarks at the end of this paper, providing evidence that cosmic rays come from supernovae, that really, I would say, Baade and Zwicky make what's, in my opinion, their biggest and wildest, and honestly, also, I'm a little bit biased because I study neutron stars, but what I think is their most impactful prediction, which is they predict the very existence of neutron stars. And it would be like another 20 years until any real impactful work was done with this prediction of neutron stars. As a matter of fact, most individuals in physics and astrophysics and astronomy really regarded this as kind of like one of those a bit more audacious claims, if you will, almost like a pet project, like one of those things that, you know, as I mingle with people in astronomy and astrophysics, it seems like everybody has that one kind of fringe, far out there thing that they believe to actually be true to some regard. They just don't necessarily have all of the pieces together to provide evidence for it or suggest it. They might have a couple here and there, but it's not really convincing. But nevertheless, in the 1950s, people started to pay much more attention to these neutron stars. And perhaps the next conversation that I do like this might be on some of that work done in the 1950s. I don't know. I'm just spitballing here at the end of the day. That's just what's running through my head. If you liked this, found it useful, interesting, entertaining, informative, educational, I don't know, let me know. Because I actually quite liked doing this. Anyways, like I said in the beginning, none of this was scripted whatsoever. I had a rough outline of kind of what I wanted to talk about and in what order I wanted to talk about it, and I had a couple of quotes highlighted from these papers, but other than that, I've kind of just been spitballing here. References for both papers by Baade and Zwicky published in 1934, the first titled On Supernovae, and the second titled Cosmic Rays from Supernovae, will both be in the description, of course, and I'll possibly throw them here on the screen for you as well. But do go look for those papers. Again, they are both available with open access from the publisher, so go check them out and read them. They're not too long. They're both about 5 or 6 pages each. I've read through both of these papers almost, I would wager almost about 100 times now in my lifetime, just because of how short they are and how quick they are to go through. And every time that I'm thinking about supernova remnants, or I'm doing something with neutron stars, I mean, most of my work is really with regard to pulsar timing and magnetar timing, and you know, basically any pulsar that's a magnetar. I'm also interested in timing, doing timing work on it. But anytime I'm thinking about things theoretically, or I just need a better understanding of something, or I'm just, you know, wrangling with an idea in my head, it's nice to go all the way back to the beginning here. And of course, as I also mentioned from before, I hope that whatever you got out of this, if you got anything out of it at all, because I don't anticipate that many of you probably would have gotten anything out of this, but if you did get something out of this, the whole purpose of why I decided to do this is because I'm not an academic, okay? I don't want to be an academic. I like doing my research, I like having fun doing the science, but I do it outside of an academic environment, and that's really what I think allows me to have fun with this here. And the one thing that I've lost by not being in an academic environment, at least for a while now, is I've lost the community of individuals that I can have these types of conversations with. And so if I can have this type of conversation here on the internet with all of you, I can't really have that conversation if it only goes one way. So if you found this interesting or entertaining, or you have questions, comments, concerns, anything at all, feel free to let me know. Of course, I have a lot of people that I still talk to about these types of things. I miss getting to have these conversations, and I think that the more people I get to have these conversations with, the better. At least those that are genuinely interested in neutron stars, pulsars, magnetars, supernova remnants, or just the supernova process. I mean, there's a lot of really cool stuff going on with this. And I think that if any of you are interested in it, this is really the best place for anybody to start. Right at the source, from Baade and Zwicky, in these two papers, from 1934. Thank you all very much for listening. If you've made it this far, if you found this enjoyable or you liked it, let me know, and I'll possibly make more of these. That said, this is Nick, saying adios, folks.